This section is on the chain rule, which is a differentiation rule. We use it almost all the time when we have composite functions. We have composite functions very often, so we have to use it with composite functions. If y is 6x minus 10, here's a simple example, then we can write y equals 2 times 3x minus 5, which is now a composite function. And let's let u equal 3x minus 5, so we have y is equal to 2u. So first, just differentiating y equals 6x minus 10. We can do that, no problem. This is just to prove this is going to work. Now let's try setting up y equals 2u. We'll differentiate that. We get dy du is 2. Meanwhile, we've got u is 3x minus 5. Differentiate that. We get du dx is 3. So let's bring the 3 down, the 2 down, the 6 down. Notice that 6 equals 2 times 3, or dy dx was equal to dy du times du dx. And you can think of that as the differentials canceling. So what happened was, if you go back to this formulation of it, you differentiate from the outside in, as you'll see. Let's go down and show another similar example. Supposing y is 5u minus 2. So let's let where u is equal to 3t. And so here we have y is all this. Okay. So if we want to get dy dt, distribute, we get dy dt is 15. Now let's get dy du. Dy du is 5. U equals 3t. Du dt is 3. And of course, 15 is 3 times 5. And again, chain rule. It's called the chain rule. So one more example. Y is 9x squared plus 6x plus 1. Now you have a composite function, 3x plus 1 quantity squared, where if u is 3x plus 1, we've got y is u squared. So you can differentiate this using power rule, and we get all of this. Y is u squared, differentiate that. Dy du is 2u. Differentiate this one with respect to x, we get 3. And bring this all the way down here. So then dy du here, well, u is 2 times 3x plus 1 because that was u. And we differentiate, and we get 6x plus 2. And then over here, we just bring these down, and you get 18x plus 6 again is 6x plus 2 times 3. So once again, chain rule works. Dy dx is dy du times du dx. Now, it's a little bit easier in general to think of this as working your way from the outside in. So let's say we want to find the derivative with respect to x of cosine squared 3x. Now there's 3 things going on here. There is the squaring, the cosine, and the 3 in that sort of order as far as differentiation. Even though it looks like the cosine's on the outside, you have to remember this squared is really squaring the whole thing. So first thing to do is to think of it like this. That's an easier way to make sure you get the order right. So outside in. So first we're going to do power rule. And we get this. Then by the chain rule, you've got to multiply by the derivative of what's inside. So now we do the derivative of this. Okay, this is fine. Derivative of cosine's negative sign, so you do the outside in, but we still have to do the derivative of 3x. We're working our way from the outside in. And so derivative of 3x with respect to x is going to be, that's 3. And then finally you write it all together like this. Now, you might wonder, why don't we keep going? You could take the derivative of x with respect to x and just get 1. That doesn't really add anything to what we've got, though. Okay, here's another example. Y is sine squared of x minus 4, x squared minus 4, so outside in. So first derivative of sine, which is cosine, and then the derivative of x squared minus 4, you've got to multiply that on. And so that's 2x, and you can just put the 2x in front. So it's another rule that you're adding on to everything else you've learned. So power rule, and then you multiply with, you've got chain rule, trig. It's just one more rule you're adding on to all the others. So here's another way to look at it. If you have f of g of h of x, this composite function, derivative of the outside, f prime g h of x, then work your way in, g prime h of x, and then h prime of x. And then if you want dx, but that's just 1. Or in the Leibniz notation with differentials, you can look at it, say this way, where the differentials sort of cancel out. But the idea is to always differentiate from the outside in. So let's take a look at several examples. And an important thing about a lot of this is factoring out the lowest power. Whenever you have situations with the radicals, it's going to be very important to factor out the lowest power to help simplify it. So first thing to do is to rewrite this in this manner. Now this is going to require product rule. So derivative of x is 1 times 2 minus 3x squared to the negative 1/2. Okay, plus, and then we've got x times the derivative of all this. So that's power rule, which is here, times the derivative of 2 minus 3x squared, chain rule. Derivative of 2 is 0. Derivative of negative 3x squared is negative 6x. So I can rewrite it like this by canceling negatives. Half times 6 is 3. Get the x in front. Now factoring out the lowest power. The lowest power between negative a half and negative 3 halves is negative 3 halves. So I'm going to factor out 2 minus 3x squared to the negative 3 halves. Factoring is like dividing. When you divide it out of this second term, you're just left with 3x squared. When you divide it out of the first term, this is where it gets a little tricky. Factoring is like dividing. When you divide with exponents, you're subtracting the exponents. And negative a half minus negative 3 halves becomes positive 1. Okay, and you can see if you distribute back, negative 3 halves plus 1 is negative 1 half. So now that we've done that factoring, well, now these two things can actually be combined. They're like terms, and it turns out they cancel out completely. And so you see by factoring out the lowest power, we're able to get from this expression down to this one, which is significantly simpler. Okay, this is sort of chain rule run amok over here, this particular problem. Sine squared of cosine of tangent of rad 3x. The function doesn't really have any use except to illustrate how to use the chain rule. So we're working away from the outside in. First thing to do is power rule. That's on the outermost thing. So our first term is going to look like this. 2 sine cosine tan rad 3x. Working your way in, now the derivative of sine, which is cosine. You rewrite all the other stuff inside. Then working our way in further, derivative of cosine is negative sine, and everything else that's still inside. Working your way in further, the derivative of tangent is secant squared. Then we got to do the derivative of the radical, which is power rule again. So we have this. And then finally the derivative of 3x, which is 3. And then if you want to rewrite it, usually we'd put the numbers in front and then the polynomial stuff and then the trig. And so it could look something like this. Not that that's really a whole lot better. Okay, here's another example already shown. So again, I'm illustrating with the u's and v's that this is going to require product rule. So we've got derivative of x squared is 2x times 1 minus x squared to the half plus x squared times the derivative of this. I use power rule, half times 1 minus x squared to the negative a half. Then chain rule, derivative of 1 minus x squared is negative 2x. Factor out the lowest power. Well, first thing to do is I can combine the negative 2 and the half and the x squared, and I get this. Okay, well, factor out the lowest power, which is 1 minus x squared to the negative a half, but also you can factor out an x, because I've got an x and an x cubed. So I factor out all these things. Remember, factoring is like dividing. So this one's going to become 1 minus x squared to the first power, because you subtract exponents, and then you'll still have a 2 left over because you factored out the x. And then this one over here, this goes away because you factored it out, and you factored an x, so you're left with an x squared. And you see, again, you've got like terms, so it allows you to simplify further to get all the way down to here, which is important when you're doing things like setting this equal to 0, which we will be doing later. Okay, here's an example of with and without the chain rule. Now, you could multiply this out and then do it without the chain rule, or you can do it with the chain rule here, use power rule, and then chain rule, derivative of 2x plus 1 is 2. Obviously, if this is to the 5th power, the 9th, you're not going to want to do it without the chain rule. This is with chain rule. Derivative sign is cosine times the derivative of 2 theta, which is 2, so I put the 2 in front. Here's a double angle formula, 2 sine theta, cosine theta. Then you don't need chain rule, but you do need to have product rule, and you get all of this stuff, which ends up being the same thing if you use a double angle formula for cosine. In this problem over here, I'm showing the equivalence of the product and quotient rules. So what you can do is rewrite u over v as u times v to the negative 1. Then we do a product rule with this. So we have derivative of the first times the second plus the first times the derivative of the second. And the derivative of v to the negative 1 is negative v to the negative 2 times v prime by the chain rule. So now we can do this with chain rule. So really, you don't have to ever use the quotient rule. Sometimes it's more convenient, but with product rule and chain rule, you never really need quotient rule. So I can rewrite these guys, u prime over v minus u over v squared, and I've just put a v top and bottom to get a common denominator, and you see I end up with the quotient rule. And cotangent you could do as cosine over sine with quotient rule, or if you wanted, you could rewrite it this way and do it with product rule and chain rule. So some more examples. Okay, this function, I could rewrite it like this incidentally if I factored out a 3 cubed. But just leaving it in this form for now, we use product rule, derivative of x is 1 times 3x minus 9 cubed plus x times the derivative of 3x minus 9. So that's power rule here, and then times the derivative of 3x minus 9, working your way in, chain rule. Factor out the lowest power. Well, I first of all simplified a little bit. Factor out the lowest power, which is 3x minus 9 squared. Always factor out the lowest power. You're left with a 3x minus 9 plus 9x, like terms now. So you can simplify further, and we can factor further. I can factor a 3 out of here, and then if I really wanted to, I could even factor a 3 squared out of there and get all the way down to this. Okay, this one's already shown. This is a case where, again, we have product rule, power rule, chain rule. So we got derivative of x squared times this one plus x squared times the derivative of all this, which is going to be power rule here, and then chain rule over here. We simplify this stuff a little bit. We factor out an x on each side because there's an x here, and again we can factor out the lowest power, which this time is to the negative 3 halves. This negative half becomes to the first power. Over here it just goes away. You're left with like terms. You've got a 2x to the 9 and a minus 9 halves x to the 9, and then this 18. And so this will simplify further. Okay, x squared tan of 1 over x. Again, we've got power rule, product rule, chain rule. So derivative of x squared is 2x times tan 1 over x plus x squared times the derivative of tan 1 over x. Working your way from the outside in, derivative of tan secant squared, derivative of 1 over x, negative x to the negative 2. These are going to cancel, and so we can simplify this a little bit, write it like that. A couple more. Okay, derivative of 3x is 3, no problems there. Now, this time the square is not over the whole thing, it's just for pi x. So the outermost thing really is the cosine. Derivative of cosine is negative sign, so negative sign becomes a positive. 5 is just a constant multiple. So positive sign of pi x squared. Then, by the chain rule, working your way in, we do power rule. So we get 2 times pi x, working your way in some more. Derivative of pi x is pi. And then you just clean it up a little bit, write it like that. And finally, I'll just show the derivative of this. The 0, negative 2 we're not going to use. We'll just say find the derivative at 0. So here I'll use the quotient rule. So bottom, put on the bottom and square it, and then write it over here. Times the derivative of the top, which is 3, minus the top, times the derivative of the bottom, which is 1. Evaluate it when t is 0. So not really any chain rule here, actually. And you plug in a value, and so you get the derivative at this point is negative 5.